what I'm going to talk about. Preliminary point is talk about some obvious facts, in quotes, and the two legs of physics. Second, it's interesting that Garnet talked about the Feynman propagator because I'm also going to talk about the path integral formulation of quantum mechanics and quantum field theory, because both can be the standard conceptualization of both is in terms of path integrals. Right? And then draw an analogy between path integrals and something that we're all familiar with, cell phones. And talk about some other analogies, some experimental predictions, and some philosophical conclusions. All right. So this is a reconceptualization of quantum mechanics. Everybody, Feynman famously said that nobody understands quantum mechanics. So this is another way of thinking about it that may be more accessible. All right, so beware of obvious facts. The Earth is stationary. It's obvious. Okay? And it was obvious for thousands of years. Solid objects fill space. That was also obvious for thousands of years. Okay? Time is the same for everyone. Okay? And events have precise locations in space and time. These are all obvious. Okay? Unfortunately, they're not true. So beware. Okay? That's the first point. All right. Now, here's an obvious fact that. Whoops. Sorry. Go back. I hit the wrong thing. I would like to make. I keep hitting the wrong thing. Too many things on it. I would like to move this. Maybe I can move the mouse. Sorry, technical difficulties here. Maybe I'll move the keyboard up there. I want to make this small. Can I make it this? Oh, there we go. Okay. So let me go back up. All right. All right. Causality. Everybody knows that the law of cause and effect. And causes are in the past, right? Things happen now, and they happen because of causes in the past. And most physical equations reflect this because they're functions of time. You have your initial conditions, and from your initial conditions, you take the function of time, and then you propagate the influence of the initial conditions. And this is just sort of ingrained in physics. But why? What distinguishes cause from effect? What is cause? I'm not really a philosopher, but I know that Hume talked about correlation versus causation. What's the difference between correlation and versus causation? And as far as I know, this problem has not really been solved. Maybe some people disagree. But this is an obvious fact, and as I said, maybe we should be aware of obvious facts. Now, there are a couple of things that are fishy about causality. I don't want to dwell on these. Just the first one. I actually made a video where I talk about these things, and I want to put up the whiteboard. Okay, where's the whiteboard? There should be a whiteboard here somewhere. Oh, I think I have to stop sharing if I want to do the whiteboard. Right, so. Hopefully we can do this. Let's see. All right, so consider Consider another familiar scenario, a clothesline, hanging from two poles. Right? And you know the clothesline makes a certain shape. I guess this is called a catenary. And how does the clothesline assume that shape? Well, it's a process of minimization. It assumes a shape that minimizes potential energy. Now, when you hang the clothesline, it doesn't it takes some time to reach that shape. Right? You hang it and it drops and it forms that shape through process. Okay? So you have this minimization, and the minimum is realized through process. Now, those are one of the key equations. One of the key ways of formulating classical mechanics is the law of least action, Hamilton's principle. Hamilton's principle is very similar to this. In this case, you fix 2 points in space, and you're connecting by a path with certain properties, and the path that is actualized is a path that minimizes. Now, in Hamilton's principle, you're fixing 2 points in space-time. You're fixing the initial point and the final point, and you're finding the path in between that minimizes something or extremizes something. Somebody said something about that. Maybe something that's easier to understand is Fermat's principle of least time, which is very similar. The idea that light will travel on the path that minimizes time from point A to point B. Right? The famous example of the lifeguard. Maybe I can go off to the side here. If you have a lifeguard out here, and there's someone, and this is the water here, and you have someone drowning here, what path will the lifeguard take? Well, he goes faster on the beach than in the water, so he'll angle over this way and then go down like that. Right? He's not going to go straight, he's not going to go along a straight line, he's going to angle. Okay. But how does he do that? Well, because he assesses possibilities. Right? He looks at the alternatives, and then he chooses this one because it minimizes his time. Now, does light do that? Does light look ahead and say, whoops, that's where I want to go, so I better go this way. I don't want to go that way, I better go this way. So there's an issue here. See, if you think of Hamilton's principle as the result of the outcome of a process, if you're fixing points in space-time, that process cannot take place within space-time. In this case, when I hang the clothesline between 2 points, there's a process in time, not in space. Right? The variation is in time, and it stabilizes in space. So it's just a suggestion that if you have an extremal principle like this, it's often the result of a process. And if Hamilton's principle is the result of a process, then it's not a process in space-time. It must be a process outside of space-time. Okay? So that's kind of a suggestive fact. And there are other suggestive facts as well. So I just, okay. Whoops. How come I'm back here? I want to go here. All right. So that's one thing that's fishy about causality. And there's some other things also, like the reversibility of mechanics and stuff like that. So, page down. All right, no. This is, this is one also very fishy thing about causality, which comes out when you look at quantum mechanics. And I've thought there's something called the Bell's inequality, and and things like that. So I think this is a very simple way of understanding what's wrong, what's the funny things about Bell's inequality in this experiment. So here's a quantum game show. Okay, you've got 3 doors. I don't know if you have games like this in UK, but they used to have games like this in US. I would never watch them. Okay. So now you've got the game show host who decides what's behind the 3 doors. Okay. Yes, Monty. Well, it's like that. Yes. Okay. Now behind each door, there's either money or car. Money. Okay. Now you have a contestant that gets to choose 2 doors. Okay. And I'm not sharing my screen. Sorry, I have to go back and share my screen. If I forget to share my screen, please remind me, because yeah, it's easy to forget. Okay, let's go back here. All right, so let's see. So let's go back here. All right, so the contestant doesn't know what's behind the doors. The contestant chooses 2 doors. Now, if the prizes behind those 2 doors are the same, they win. Otherwise, they lose. Okay? I think it's pretty clear what's going on, right? If the contestant chooses the red and the green door, and they're both money, he wins. If they're both car, he wins. One's car and one's money, he loses. Okay? And the contestant can choose any pair of doors, completely free. Okay? So they played this game thousands and thousands of times, and people discovered that if the contestant chooses 2 adjacent doors, he will win 85% of the time. Of course, this is not realistic usually, but that's what the contestant has observed. what people have observed. The two adjacent doors, if you choose two adjacent doors, you will win 85% of the time. All right? Now, the question is, what can you say about the case where you choose the non-adjacent doors? What can you say? Well, you can argue like this, and this is a correct argument. You can work it out in detail. You can draw you draw a set diagram, and you can verify that this is true. Now, if red and green agree 85% of the time, they disagree 15% of the time. Blue and red also disagree 15% of the time. So that means that all three must agree at least 70% of the time, because they disagree at most 30% of the time. You may not be convinced by my verbal argument, but if you work it out, you'll see that that has to be true. All three must agree 70% of the time. All right? So, does that make sense? All three must agree. So that means that if all three agree 70% of the time, and I choose the two doors on the end, I must win at least 70% of the time. Right? Did I get some buy-in or not? Or should I do the argument? Maybe I should do the argument so it's more convincing.
When you say all three must agree,
yes,
you mean that 70% of the time there is the same thing behind
yes,
three
that's
doors?
right. That's right. The game show host can choose anything to put behind the doors. Right? He's free to choose. So in that case, the deck is stacked. They'll win no matter what, right? But if the game show is played this way, such that 85% of the time you win with any two adjacent ones, it must be true that at least 70% all three agree. And you can draw the set diagram and see that.
I would have thought it was 85%.
Well, you can. That's at least 70% of the time. I mean, you can. It might possibly be more. All right. So if you got this, you do this set diagram, and you say this is the space of all possibilities. Now, 85% of the time, red and green agree. So R and G agree here. So they disagree this amount of time. So I'm representing R and G as a subset of the entire set. Okay. And it occupies 85%. Now I also know that, what was the door in the middle? Red, right? Red was in the middle. Okay. So that means that red and blue are the other two adjacent. That also must occupy at least 85% of this space. Okay? So I don't know, can I make another color? I guess I can. Where are the colors? Well, I don't know what's going on, so I don't want to waste a lot of time. All right. So that means that you have to choose another set, and the intersection of these two sets is the set where they all agree. Right? Now, the area of that set where they all agree is at least 70% of the total area. Because, in fact, if I choose, let me do it this way. If I choose one set here and another set here, then the intersection is exactly 70%. And that's the lowest possible. Could be more, but it's at least 70%. Now, when you actually do the experiment, well, all right. So so suppose you're observing this game show.
You won't share?
Yeah, okay, yes, thank you. I think, no, I'm actually still sharing. For some reason it started to behave. Okay, I don't know why, but
70% of the time it behaves.
okay, oh, sorry.
70% of the
Yes,
time.
yeah, no, but in fact, all right, now suppose you observe this game show and you find out that in fact they only agree 50% of the time when they choose the ones on the end. If the contestant chooses two adjacent ones, 70%, 85%. But if he chooses the two on the end, he only wins 50% of the time. What's going on? How could that possibly be?
Because adjacency all the way plays a part in it.
If you're a host show and you know the statistics, you could falsify it. Because you could put the same objects at the end doors and then your argument falls.
Well, if you put the same at the
Yeah.
but you don't know what the contestant's going to choose unless you can guess what the contestant's going to choose. If you put the one that's different in the middle,
Yeah.
then he might choose the two adjacent ones, and that would drive down the probability.
Yeah.
So what must be going on?
Obviously, probability is affected by whether they're adjacent or not. We're looking
Yes,
at
okay,
three
yes.
separate doors.
Yes. Okay. So in practice, what would that mean?
It means they're not equal.
Well,
Well, no, they're correlated.
well, it means that the game show must be cheating.
Yeah.
You know, as soon as he finds out the choice, they pull a fast one and they switch. That's one possibility.
There's got to be a correlation when you choose one, the one that's adjacent to it automatically changes.
Something like that. Yes, that's right. So that's cheating, right?
It's not cheating,
Right.
we'll do it.
So yes, okay. Another way around it is to say that somehow both the game show and both the contestant and the host are being controlled by some higher power, and that somehow they're coordinated, so that if the game show host, if the contestant chooses something, the game show host somehow thinks in a way that arranges the things behind the door. But you can do this. You can simulate this. There is no way of making this happen. There's no way of disagreeing less than 70% of the time, unless you cheat. You can run on a computer. There's no way to do it. Okay. All right. So the conclusion is either the game show host is cheating and he switches, or the contestant and host are somehow mysteriously coordinated. Now, if they're coordinated, then the game show host doesn't even need to put something behind the third door. Right? There may not even be anything behind the third door, because if they're coordinated, the contestant will always choose the two that the host has in mind. So there may not even be something behind the third door. I think you mentioned Sabine Hossenfelder, and she calls this the superdeterminism, that what we call the cause, the event, and the measurement are somehow mysteriously synced up somehow.
What's the name of it? Is it Darren Brown? The guy who did, there's a magician. I mean, there are various magicians
Yes.
who will, work on people's minds.
Well, yes. Okay. Okay. But that's
Shed
all
or
right.
noise.
All right. Now, I just say that there is an actual experiment where you have circularly polarized photons, and you can measure them in different ways. The red represents the door in the middle. The green and the blue represent the two doors on the side. The experimenter can choose either to choose the red or the green on the left, or choose the red and the blue on the right. And you get these same probabilities if you do this. If the experimenter can choose randomly, can choose after the photon has left which one he's going to pick. And I think they've done this experiment several times, and the results are exactly what I said. If you choose the red and the blue, 85% agreement. If you choose the green and the red, 85% agreement. If you choose the green and the blue, 50% agreement. So that's one obvious fact. Second obvious fact is we live in a universe where objects, i.e. particles, move through space for space-time. I mean, before we knew about particles, we had large objects that moved through space-time. And we found out, no, those large objects are actually made up of smaller objects, which are actually made up of smaller objects, which are actually made up of smaller objects. But basically, we have objects moving through space-time. Of course, we also have light, and a photon is kind of like an object, but it's also moving through space-time. So that's what we think. Right. Now, there's this other experiment that's kind of cool called the quantum bomb detector. And this actually has been done. It's not fiction. And this one is a demonstration. I think I give the website there, kind of a simulation. So it's set up as follows. Okay. All right, so what you're doing is from the lower left here, you're sending out a photon. And that photon goes through a beam splitter, a half-silver mirror. The beam splitter means the photon half the time goes one way, half the time goes the other way. So the photon can actually follow two different paths. It can go up, well actually more than two different paths, 4 different paths. It can go up, down, up. You can go up, down. So you can see it makes two choices, basically. Right. Now, if you know anything about waves, you know that you can arrange waves so that there's destructive interference, so that two waves will cancel out. So you arrange the second beam splitter so that if both paths are open, then nothing can get to detector 1. Because if it got to detector 1, you'd reach destructive.
I'm not seeing the talk at the moment.
Okay, good. Thank you for telling me that. And I don't know why. So we'll try this again. I think it's here. All right, I think. All right. So if both paths are open, then nothing can reach detector 1. Wait a minute, I'm saying, let me see, did I say that right? Yeah, both paths are open, nothing can reach detector 1. Now, if, let's see, now you have this case where you put a bomb here, and this bomb has a photon detector. Now, if the photon detector is working, then the lower path is blocked, right? The only way for the photon to get through is to pass through the photon detector. It's blocking the way. The photon detector is not working, the photon passes through without problem. Okay. So that you don't know. So you want to find out whether the photon detector is working or not, without exploding the bomb. Now that seems hard to do, because in order to test whether the photon detector is working, you kind of have to send a photon in there, and if you send a photon in there, then tough luck, you're gone. Okay? All right. Now it turns out that quantum mechanics predicts, in this setup, that in fact, if you do have a working bomb with a working photon detector here, in this lower bomb holder, 50% of the time the bomb will explode when you send in a photon. 25% of the time the photon will come out at detector 2. 25% of the time the photon will come out at detector 1. Now what does that mean? If the photon detector is not working, it can't go to detector 1. It's not possible. It will never go to detector 1. But if there is a working bomb in the bomb holder, 25% of the time, you can detect it without exploding. So the photon both goes through and does not go through the bomb. It has to go through because if the bomb wasn't working, there's no way the photon could go to detector 1. So it must go through somehow. But on the other hand, if it went through, it explode the bomb. But it doesn't explode the bomb, and it still gets detected, but the bomb has to be live. And as I said, this has been experimentally verified. In fact, you can make a more sophisticated arrangement to improve the odds. You can improve the odds arbitrarily large so that you can detect the bomb with arbitrary high, probably close to 1. So, what's going on here? I mean, so what's strange about this? What is really strange about this? And what's strange is that we are conceiving this process as a process in which particles are moving from point A to point B. If you conceive of this in those terms, it doesn't make sense. If you don't, it makes sense. This is what they call this what it says, non-interactive observation. So I'll give you an example. I was sharing an office with my colleague, and there was a mouse in the office. Right? Now, we never saw the mouse, but we can see what the mouse did to the trash can. You know, it's to take stuff out. So that's a non-interactive measurement. I don't have to see the mouse. I don't have to contact the mouse. I don't have to have any direct. And the mouse doesn't see me, right? But I know the mouse is there. Not a problem. The problem comes because we think that it's that the photon detector is an object moving from point A to point B. So there's some issue about that, well, something suspicious about that picture. That matter is fundamentally particles moving around. It's another obvious fact. All right. Now, so these are fireflies. I suppose you have them here in UK, do you? Mm-hmm. Okay. So this is in southeast US, and this is a time-lapse photograph. All right. Now here you see this is a time-lapse photograph. So these are not all at the same time. So in fact, I have this flash, and then this flash, and then this flash, and then this flash, and then this flash. What's going on?
Firefly in motion.
That's one possibility. But there's another possibility.
Multiple fireflies.
Yeah, that's right. There are two possibilities. How can you tell?
From the evidence.
Yeah. Well, no, you need more evidence than this. Right?
If you've got multiple fireflies, it's unlikely they'd be traveling in a straight line.
Well, maybe they're on a branch. Okay, so yeah, okay, I get that point. But if you watch enough of them, it may just happen by chance. But you get my point. There's nothing that we can see that can definitively determine the difference between those two. So the bomb detector experiment, is there really something traveling from point A to point B? Or are we just getting two flashes? All right, so that was my first part. Second part, physics walks on two legs. There's the conceptual or analogical part, and there's the mathematical part. And there are many, many examples of this. For instance, you have PD equals nRT, right? And this was a empirical relation, mathematical relation. And from that, people thought of the kinetic theory of gases, where you have particles moving around. And that's a conceptual model, right? You're thinking of the gas as basically billiard balls. So it's the conceptual model, the analog, that drives the mathematics. But the mathematics can also drive the analog. Right? One famous example of that is black-body radiation. Planck had Planck's law, and it was an empirical law, and then Einstein came along and said, well, this is explained by quantum. So you really have two legs. You've got the analogy leg and then the mathematical leg. The analogy leg suggests a mathematical model. Then when you find the consequences of the mathematical model, that suggests other analogies. So it's two legs like this, taking alternate steps. Now, I would say that I think one of the reasons that a lot of us are uncomfortable with quantum physics is that we've been hopping on one leg for the past 100 years. We've just been developing the mathematics without any conceptual model that matches that. Or there have been different attempts, but none has consensus, and all of them seem kind of, well, maybe unsatisfactory. So I think, I think some people, like the Bohr school, says that's all we can hope for. We have to keep hopping on one leg. There's no analogy. There's no way of understanding this. It just happens. You know the famous quote: "Shut up and calculate." You just have to do the math, and whatever the math tells you, you have to do that. But that's very unsatisfying, because I think that the essence of understanding is analogy. When you say you understand something, it means you relate it to something that you're very familiar with. And in fact, if any of the spiritual teachers do the same thing. Like if you talk about Jesus, he says, "I'm the bread of life." You know? And he says, if you believe in me, rivers of living water will come up from within you. These are analogies, right? And you have to know how to take them. I mean, rivers of living water does not mean that there's a chemical formula and it has, and so you have to know how to take it. But it says something to you. It means something to you. And like also, say the picture of gases, very beautiful picture of gases as billiard balls. bouncing across each other. Very visual, very intuitive. I grasp that, I get that, I understand that. But quantum mechanics, it's not there. You just have Schrodinger equation, and probability is the square of the amplitude of the wave function. It's just there. Live with it, deal with it. Okay, so can we take a step in the other way? That's my question. Okay. All right, now, I suggest that to take a step with the other leg, rather than using the old obvious facts, we should start with the mathematics and derive a model from the mathematics, rather than kind of rehashing our old ideas about causality, trying to take our old ideas of causality and particle and make them fit within quantum mechanics. Let's just start with the mathematics and see what it suggests. Now, if you look at the most comprehensive mathematical description of quantum mechanics, you get to the path integral. You have action. So if you can explain, if you have something that explains the path integral in analogical or intuitive terms, then you have something that really can explain quantum mechanics in the sense that it gives an analogy, it gives a picture, it gives something that I can hang my hat on. So that's what I want to do. I will start with the mathematics, and I promise you I'm not going to scare you with math. I think I only have one slide with equations on it. So maybe two. All right. So here you have, so this is what, now after Garnett's talk you probably want to change this picture, but I didn't have the benefit of this talk. So here's a path integral, and here's the propagator. And Feynman's principle says that the propagator, so from Garnett's talk you know that propagator means that I take a sum over alternative paths from point A to point B, and you basically sum up the influences, and you get something that relates A to B. And you can write that mathematically over here, which is, this integral is basically sum. I'm taking the sum of all these different paths here. I'm taking the effects of all these different paths and adding them together. And each path has an effect that is related to an exponential function with imaginary, which seems kind of strange, times some function of the path. And so I don't want to get too much into this. Okay. So I'll just say that if maybe some people have heard of Poincaré, and he calls this the equation of everything. This is basically the same idea. It's just a more complicated version. This part here is the sum over paths. This part here is the sum over paths. And here's the exponential. Here's the imaginary. And then here's this function of the path. No, it's just a more complicated idea. But I want to focus just on the idea that you're taking a sum over different paths of something related to a complex exponential. So, what does this suggest? I think to most people it suggests nothing. But it's interesting that in physics, someone talked about Wick rotation. I don't remember. I think that was a lesson. That physicists said, "Oh, we've seen some exponentials before. That's a partition function, but it doesn't have an I in it." So they take out the I and they relate quantum mechanics to statistical mechanics. All right, I want to leave the I in there and try to relate this to something that has that. And what does this get you? This gets you a wave function. And what does this wave function get you? Well, if you take the square of this wave function, I'm fudging a little bit here, but if you take the square of this wave function, it gives you a probability. So the wave function itself doesn't tell you anything. It's just the square of the wave function that gives you the probability. What's waving? Who knows? But the square of it gives me probabilities. Okay. So it's strange. It's strange. So I want to give a way of conceiving of this that makes this not so strange. Now, part of this comes from my own background. I worked for several years as a systems engineer in wireless communications. And in fact, it struck me that in wireless communications, you have something very similar. so here you've got your cell phone tower here, and you've got your cell phone. Now, what signal does the cell phone receive? Well, there's signals going everywhere. They're bouncing off people, cars, buildings, etc. Each one of these makes a different contribution. And these contributions come together and they add constructively, or destructively, and etc. Now, these are waves. They're waves traveling through space. Waves have a frequency, they have an amplitude, and they have a phase. Now, this phase is related to cosine and sine. Now, if you're an electrical engineer, the way you represent these waves is not with cosine and sine, but with complex exponentials. So I don't want to get too technical, but what you do is you take this expression and then you take the real part. It's much easier to work with complex exponentials. The complex number expresses the fact that waves have a phase. Waves have an amplitude and a phase. If you've taken physics and you've taken electronics, you know that that's how they represent currents and so on. There's complex current, there's complex displacement, and so on. Everything is with complex numbers. So complex numbers are real. I would suggest that complex numbers are just as real as integers, because I can show you a complex number. I can tell you that wave is a complex number. I can tell you what complex number that is. That I probably shouldn't have said that because it's going to be very controversial. Okay. So here's all right. So there's a little bit more. So anyway, this phase means that there's the phase expresses that there's a cosine part and a sine part, so that gives you real and imaginary. There's more to the picture, but and I don't want to get into the details, but to just say, all right. So consider this scenario. Suppose you have a very, very bad signal, and your cell phone needs to register. Your cell phone needs to detect the tower. So you're in a room here, and my cell phone needs to connect with the tower. Now, what actually happens? You carry your cell phone around the room, and you're trying to find a good spot. Now, what's actually going on when you're doing that is that the cell phone is accumulating signals. It's accumulating a signal. It's looking for a certain kind of signal. So it's accumulating. It's accumulating the signal that it's trying to detect. And when it reaches a certain threshold, then it registers. That's when it registers. So here we have our cell phone wandering around in the room, in different places. Now the signal may be stronger here than there. The signal may be stronger in one place than another place. The question is, where will the cell phone, and you have, maybe you're wandering around for days, okay? So you may go and you come back, right? And then finally your cell phone registers. Where are you when the cell phone registers? Well, you don't know for certain, but there's some probability distribution. Okay? It turns out that the probability distribution of one of these squares is proportional to the square of the complex amplitude of the signal at that point. It's the same mathematics. And that complex amplitude is due to the sum of paths from various sources. Exactly the same basic picture. And this is a process. Right. So here I'm just saying, I just said what this says. So I'm passed by so as not to scare people. Right. So I want to try to draw a comparison between this and what could possibly, and in a picture, an analog that can explain what we see. All right. So the cell phone moves randomly in space as a function of time. Now, as I said before, if what we see in space-time is the result of a process, it cannot be a process in time. Because the locations are space-time locations. So it cannot be a process in time. Because if I pass through the space-time location, I can't go back. So it must be a process in another dimension. So what I'm saying is, there's a configuration, there's kind of a pre-space-time that moves randomly as a function of a non-space-time parameter. Okay, so I'll just call that the process dimension. So the picture is not that the universe is a process that's unfolding in time. There's a process, and the space-time, all space-time, all space, all time is an outcome of another process. Right? And this goes along with a picture of space-time as a unit. I mean, Einstein said space-time is curved. It's a unit. They call it block space-time. So I'm saying that the block space-time from the Big Bang until whatever happens, that's an outcome of another process. Right. So let me see. Let me not go into the details, but I think that's the basic connection that I want to draw. And we can have, if people want to have questions, we can ask questions. Okay. All right. So now here's where we relate to the bubble. This is exactly where we relate to the bubble. Okay. Actually, I think this one is in Britain. Maybe we can watch this too. I don't know if you people can see this. But this one was nice too. Okay. I'll just accept. Won't let me accept. Okay, here we go. Alright, so it says this is Snowden. Okay, it says Alright, now what's going on here? Alright, you have a process of bubble formation. The bubble distorts and changes shape, right? And at some point the bubble pops. Okay. What's the shape of the bubble when it pops? What's the shape of the bubble when it pops? Well, it depends on the process that it went through to get there. Now when the bubble pops, you see it's kind of like, it looks like a process, right? It starts popping at one point and then it goes, that's time. That's our experience of time, in an analogical sense. Okay? So that's what I'm saying is an analogy, an illustrative analogy that makes sense. All right. So as I said, there's a process of formation. At a certain point, the bubble breaks. The shape of the bubble depends on the entire process, and bubble breaking is a process itself that reveals the result of a previous process. So the process of the bubble breaking itself is not the fundamental process. It's kind of a derivative process that depends on the previous process. I guess it's still running. Let me stop. All right. So another example. When I was a little boy, we would go to the seashore and we see the fishing boats come in. It always fascinated me that when the waves break on the beach, it looks like something is moving down the beach. It looks like there's an object moving down the beach. But of course it's not an object moving down the beach. It's coming from somewhere else. It's just, a physicist would say group velocity and phase velocity or something like that. But it's not an object. So what I'm saying, what we call objects are something like this. Okay. There's a correlation. There's a correlation because they have a common source. But the source is outside of space-time. So it's interesting that Newton said, I feel like a little boy playing with pebbles on the beach, on an unknown beach. So the space-time universe is the beach. And the unknown is not in this space-time. It's a process outside of space-time. Right now, when I wrote this original paper, I compared it to Many Worlds. I don't think Many Worlds is very popular among the people here. But you may know that Many Worlds is an interpretation. So this compares the picture I'm trying to explain versus Many Worlds. And the picture I'm trying to explain, here's the process dimension is this way. The universe is a slice. So this is a 0 space plus 1 time dimensional universe. So this space-time universe is a point in time. And it has 2 states, red or green. And it alternates between the red and the green. Sorry, I can't draw, I would like to draw a higher dimension of space-time. It's an analogy, okay? It's an analogy. So, and I'm not an artist. Okay. So you can see that the alternating between red and green that is observed in space-time, it comes from these red and green bubbles. You know flat land, right? It's the same idea, that there's something, it's a slice of a higher dimensional reality. What many worlds says is that actually when something changes, the universe actually splits. So this is Swiss cheese and this is spaghetti. So take your choice. I think topologically this is a lot easier. I mean, this really gets very hairy very quickly. It's like Medusa's hair. It just keeps, the worlds keep multiplying. Well, anyway, since people here don't believe in many worlds, that's fine. All right, so there is a prediction of this point of view that since this is a process and it's a random process and there's some jitter, that jitter will introduce some small correction. And that small correction should affect events of low probability, should increase the probability. So I would suggest that the Schrodinger wave function, where you have interference and you have nulls, the nulls are not really nulls. That there's a non-zero component due to the jitter. So, all right. So here are the conceptual consequences, and maybe I can slow down a little bit. And I don't know how much time I have left. How much time do I have left?
10 minutes,
10 minutes,
including
okay.
questions.
Okay. All right. Good. So I'll just pass through these quickly. So I have the model, and this gives a physical interpretation of the quantum field. It's not merely a reflection of partial knowledge. It's a reflection of a process that is going on. It's just a process that we don't have access to. Temporal causality is an illusion. I don't call it causality because it's not in time. Something outside of space-time is doing the causing. So, so you can make a causal theory if you move the causes outside of space-time. Okay. So, and also there are no causes without effects. The famous question: does a tree fall if there's no one there to hear it? The answer is no. The tree doesn't fall. There's no objective reality apart from observation. The observation and the event, they're part of one whole. There's no object that travels between detections. Entanglement is uncovered and not produced. Entanglement happens because any space-time has to satisfy certain restrictions. And that has to carry on no matter where the slice is. There's a famous quote that space-time is a boiling sea of particles and antiparticles. And this picture says no. You're just seeing the vestiges of a process that happened previously not in this space. Okay. So the quest for a theory of everything is a rainbow chase. I think you can see that in physics there's been a process of successive reconceptualization. Wittgenstein has a quote that says, any kind of concept is like a ladder. You use it to climb it and then you throw the ladder away. You don't carry the ladder with you. So this is a ladder. Okay? At some point it will be thrown away. You use the ladder, you refine the mathematics, you get another ladder. So don't get fixated on a theory of everything. Okay? So physics explains almost nothing. All physics is this one slice. But there's all this stuff going on before and maybe after. Maybe it's just one slice and the process is continuing. Okay? So Hamlet said to Horatio, there's more things on heaven and earth than it dreamt of in your philosophy. So, all right. So I think I'm very interested in Garnett's picture of the Dirac propagator because I really haven't addressed that. And people have been talking about the different fields, like you talk about the octonians and things like that. I didn't even address that because that's all tied up in the phase function. So I don't even talk about that. So I would like to. That would have something to do with the nature of the signals that are being involved. In the example I talked about, you can have signals that have polarization. So polarization can produce these kind of multiplications. All right. So that's my final quotes, and I'm done.
Thank you very much for that, Chris. And we now, can we get the Rogues Gallery, yes.
With apologies.
So, question, are you saying that you would think of what happens in the path integral as part of the multiple processes that happen in the process space that you're thinking of?
Yes. I think that I'm not really sure about this, but there was someone who came up with path integrals before Feynman, and his name escapes me. He's a Swiss.
Schwinger.
No, not Schwinger. Somebody else. Don't remember his name. I'll look it up. But he said the integration was not, the integration was in another parameter and not in time. So the answer is yes. I mean, take my analogy that well, I have to take my analogy seriously.
Yeah. So then it provides an alternative to many worlds, which seems absurd to many of us.
Yes, yes, it does. I mean, I think many worlds is embedding reality in the wrong space. It's like trying to fit 2 dimensions into 1 dimension. So he's trying to make each world be separate. So yeah, so that's true.
Well, I think the mathematics I developed, the spaces are there. They're there as gauge spaces. It's split quaternion space and quaternion space itself. And we've got the equations of motion within those spaces. So you've got your space that's not within space-time. And light itself cannot be within space-time because it travels at the speed of light. And nothing travels at the speed of light in space-time. So it would seem that light itself is in split quaternion space or quaternion space. I think split quaternion space is the one.
All right. So, Louis, I think that what I said was wrong. I think that the path, when I showed that picture with boxes, the path integral takes place in each box. Because in my analogy, I'm saying that the path integral is like multipath. The multipath determines the signal at each point. So I actually have worked out the mathematics of this. There's a paper when I share the. It's actually at the beginning of my talk, but it's on archive. I worked out the math and I simulated it, and it works. Yeah. So there is some math. I do create a probabilistic model, and I show that the probabilities work. But I don't want to get into this detail.
You might have to share a screen.
Oh, okay.
Chris, I have a comment. Can I start now?
Yes.
This is Mike Horner. You mentioned the well-known story about if there's a noise in the forest, is there anything happening sort of thing?
Yes.
Now, there are people who deal with this question in a slightly different way, and it ties up with the idea that individuals cannot really guarantee that when they say this is red, that they're actually meaning in some sort of universal sense the same. So the idea, there's, let's say, an object, you might be staring at the sun, say, and then you look away from it. There is something which exists, but when you looked at the sun, you have learned in the same way that Andrew taught us to learn to understand the letter A and the number 2 and so on. So your understanding of the red sun is the way that you build that image in your mind from, I'm not quite sure what to call it, but let's say that which exists but prior to your perception of it and then your processing of whatever you perceive. And so when John Williamson looks at it or Lou looks at it, then the thing is still there, but you cannot really say it's the same thing. But it does mean you can answer the question, there is something there, but you can't say or even describe by analogy exactly what it is. So this is the perception reality as opposed to does reality exist in a sort of different sense, okay?
Well, I don't know.
So you're going to identify a thing with a process situation that will produce a perception.
Yeah, that's right. Yeah.
Well, I don't know what reality means. I think that's one of those obvious facts that I don't know what is meant by reality.
Okay, Thank you very much, Chris, because we need to move on to the final speaker of the day so we can leave the building in a reasonable time.